Okay, good afternoon, everybody. And I like to position myself a little bit before I start the presentation. As you can see, I work for the DuPont company, or should I say still the DuPont company, and we do not produce TiO2 anymore. The TiO2 production went to the Chemours company, so I am just here talking as a genetic toxicologist with a lot of experience of gene tox testing, also from TiO2. And let me state already now before I start that I actually like regulations and guidelines. So, to go to the topic, assessment of TiO2 genotoxicity, this is the major question that really looms in the room right now too. Is TiO2 genotoxic? And it could be very nice to give an answer right now, yes it is, no it isn't, and let's all go home. But that's not the case, and I will kind of take you on a journey of TiO2 genotoxicity and also try to conceive the concepts that behind all of this, because I think people who aren't genetic toxicologists may not really understand where we're coming from and what the heck the problem is here. So my focus is going to be on the ANSES review of genotoxicity and beyond. This is, of course, something that has been mentioned already. TiO2 was also reviewed for the CLH report, and it was considered to be inconclusive for germ cell mutagenicity. Important point that David Kirkland already brought up, that the focus has been a lot on carcinogenicity, but for genotoxicity there are other endpoints to take into consideration as well. One reason I focus on ANSES review is that I started to look at the publications of TiO2, very quickly realized that ANSES already did the job for me. They had done an excellent review of the gene tox data out there, and I realized that this is probably, for the time being, the most important document we have on TiO2 genetic toxicology for the moment, since it's actually up for regulatory consideration. So, a conclusive classification for mutagenicity was not possible. And here you can see the ANSES expert disregarded any data published prior to 2010, which I would have done as well. That included probably some of my own publications. The expert review included only studies published between 2010 and 2015. They looked at the most reliable data. There were unexplainable discrepancies in the data caused by physicochemical parameters, different study protocols, undefined factors. There was an abundance of data, but ANSES still concluded that more data is needed, which of course might sound like this very common end of every paper. More studies are needed, further studies are needed. At this point, I would still have said, why do we need more data? But when I'm coming to the end, I think I absolutely agree with ANSES even in this. So TiO2 is an inconclusive mutagen with potential impact. And since the 1B carcinogenicity classification was looming up front, I believe there is a risk that this was a little bit ignored. We have to remember that gene tox predicts mutagenesis, carcinogenesis, germ cell mutations, heritable diseases. We do hazard classification for GHS labeling, which of course is the global harmonized system, which for a global company actually is far more important than the European classifications they play in, but that's not really what decides what go on the label. Gene tox provides data for mechanisms. They do make up training sets for computational toxicology and for read across and grouping, so it has a huge impact. CLP inconclusive cannot be classified. Well, this might be a problem, frankly, because when you cannot classify, you still might have a possible statement about the data existing on your SDS sheet. There was a note in the ANSES document that there was also a positive Ames result, which was mentioned. This might lead to a warning labeling notification in some regions. We just have the situation for another material in Japan, where there is one positive Ames result, and they are labeling it as a class 1 germ cell mutagen. and this is just a comment about the Ames assay in case somebody likes to look it up. This is the GHS hazard classification categories for germ cell mutagens. So we are definitely not in a 1 area. We're not in a 2 area here. We cannot say it's not classified. We're right down here. Could not classify. However, I do believe that if you would take the same data package, give it to 10 genetic toxicologists of, I understand now, perhaps questionable merits, they would probably come up with different conclusions. Not unlikely, oh, this has to be a class 2 because there is so much data, there is positive data and negative data. How can you say nothing is going on there? However, ANSES' conclusion was that it could not be classified. So, in conclusive, still supporting proposed CLP carcinogenesis 1B classification. I am not going to talk now about the secondary genotoxicity. It has been discussed much and might come up even more. There was also the suggestion that it might be a primary genotoxin inducing irreversible direct interaction with DNA, and that this possibility cannot be excluded. The conclusion in ANSES' document was pretty much driven by the nanoform in vitro COMET assay results. This is a little bit my own conclusion, but I think it was also mentioned in the document. If you look at the COMET results, there were a total of 76 out of 125. 65 of these were nanoforms. There is also positive micronucleus results from the in vitro assays, but to a lesser extent, even there about half was nanoforms. And here is a statement about the data and the forms of TiO2. All forms were taken together as for the carcinogenesis evaluation. However, the gene tox results were definitely driven by the nanoform. Nanospecific effects, do we have them? Yes and no. We don't know, I guess. However, there is a societal perception that engineered nanomaterials are inherently hazardous for health and environment. Regulatory acceptance is needed both when it comes to the hazard and risk aspects. The data interpretation is difficult. Toxicological and scientific principles are often ignored or hard to apply. The relevance of exposure is often very hard to estimate. There's a question of intracellular concentration, and then the intranuclear, which I think is a concept that was pretty much introduced for TiO2 with this document. This is a little bit the street view of nanomaterial safety. This is a cartoon from the web, and people's concern, if they have a concern, seem to be that nanomaterials are small enough to kind of match the sizes of our biological molecules, and they can somehow get in there and disturb just based on the size, which is partly true even from a scientific point of view. There is material commonality and differences. There is the bulk versus the nanoform. Now, as I mentioned, I'm coming from DuPont. We are running still an in-house testing lab. We test a few hundred compounds a year, I believe, all things considered. And we try to have the approach to all materials that whatever is brought to us, we handle it the same way. There are many similarities that are listed here. Chemical species is, of course, an issue. If you look at bulk, particular, nano, is this still the same chemical species or not? I think some people would say yes, other people would say no. You look at different endpoints, the strategy should be the same. There is the OECD test guidelines. Characterization of the test material would be needed. How do you formulate your doses? The exposures in vivo, route inhalation is the most common, of course, for TiO2. Organ is lung. Exposure in vitro would be intracellular. Here we're coming again to this intranuclearity and the question of the shape and the surface properties. What impact do they have on the results we get? Once upon a time, we thought it was very simple. We would have co-culture models, and we would replace in vivo testing with in vitro. So for in vivo, if we target pulmonary epithelial cells and macrophage on the surface of the lung, we would do the same in vitro. we would have a co-culture model that would mimic the cell-cell interaction of epithelial cells and macrophages, and it would be a nice route to walk down. However, this didn't really turn out to be this way, and at least in our hands, our co-culture experiments haven't worked any better than any other in vitro experiments. Testing of TiO2 is challenging. The test guidelines and the methods for genotoxicity assessment are based on assessment of bulk materials. There is a lot of effort ongoing to evaluate and develop the appropriate tests and guidance for tests of nanomaterials. There are even people from agencies who do consider the test systems we have today to be inadequate for testing of nanomaterials, and we would need new test systems. I can't really take a stand one way or another because I haven't tried any alternative test system. Shape and solubility is an issue, and if you look again at, for example, this picture, which of course is a simplification for an audience like this, the question is, what are you supposed to test here really? The sizes differ, the shapes can differ, the composition can differ, you might get assemblies and aggregations. So we still don't know how to assess nanomaterial genotoxicity. Nano is different. There is established methods, process and paradigms. They don't always work. There is a lack of acceptance of scientific methods and principles. I think that was mentioned just a few minutes ago, actually, how any positive result tend to overshadow even many negative results. There is really no consensus about methodological revisions. There are many ongoing, not coordinated and not harmonized activities at the same time, which makes things even a little bit more confusing. Single data sets get a lot of attention, and genotoxicity is actually a very good example on this thing with the results. We accept the positive results, probably thinking that something must be going on. How could we have created a positive result? There was this big nanogenotox project, which was an EU joint action, which was also led by ANSYS, I believe, which was published in 2013. The outcome from this one was also inconclusive in a way. There were in vitro and in vivo negative and weak positive results for TiO2 and some other nanomaterials using the COMET and the micronucleus assay. There have been many other efforts as well. And there is a growing list of publications. What's kind of interesting here is if you can see here in the beginning, we get up to 2010 and there's like a stop. And then 2013, papers start to come out again, 2016 even more, and it could go on and on. There are special issues, and here are papers on the grouping of nanomaterials. There's the Nanogenotox project. There was an article on REACH, nanosafety by Harald Krug. And there is, of course, the OECD link. What happened here between 2010 and 2013 was really that people sat down and started to think, what should we do differently? Because these earlier publications reviewed lots and lots of papers and came up with the conclusion that we can draw a conclusion. So it's exactly the same as what ANSYS came up with for TiO2. Well, I was preparing this presentation. I wanted to Google something, and to my horror, I got this email, which was coming out right now in this time frame, listing even more papers on nanomaterials and TiO2. I get back to this a little bit later. I had the same experience a few months ago when I was preparing another article. There was more new information coming in than you had time to capture. For the in vitro and in vivo genotox testing, we do, of course, know what endpoints to assess. We assess gene mutations, clusterogenicity, and anagenicity, and we look at in vivo DNA damage with COMET. But note, what we do in a regulatory setting, we do the in vivo assay, we do not do the in vitro assay, really. There are methods to use, we have to give an interpretation to the data, catch incorrect results, and use the weight of evidence that has already been mentioned a few times. This is kind of a very nice cartoon. In my opinion, it shows the whole way from DNA effects to chromosomal effects to the cell, and then perhaps even to the internuclear effects. Methods, which I like, and guidelines, which I like even more, are mainly the OECD test guidelines. I put the AIMS guideline in red here because it's not recommended for nanomaterials. Still, we do use it because we kind of have to. It hasn't really been replaced by anything. And I think there is also people who still think that it might be relevant for some nanomaterials. These are not all guidelines that exist, but these are the ones that are used a lot. And again, as you can see, the one that's missing, there is no guideline for the in vitro COMET assay, which was very much used in the TiO2 document. Sadly, the OECD guidelines do not really give guidance for nanomaterial testing. This is a sentence that actually in the guidelines for manufactured nanomaterials, specific adaptations of this test guideline may be needed, but are not described in this test guideline. Furthermore, there is an overview document that came out this year, which is a guidance document to the changes made to the OECD test guidelines. And this one also has a chapter on chemicals that require specific approaches. Nanomaterials are one of them. Guidance for these special chemicals is not described in the test guidelines. So if it wasn't clear before, it's clear now. In other words, you kind of had to find out on your own how you best could test your nanomaterial. So back to ANSES, the report, and beyond. TiO2 was considered inconclusive for classification of germ cell mutagenicity. And I kind of like to point out again this thing with germ cell, because I don't know if this is going to lead to something or not. It was not considered not classifiable. Is this going to lead to further review, for example, of developmental and repro endpoints? So I just want to have a message to everybody that just don't only focus on the carcinogenesis aspect of this. ANSYS review, which was very good, was data mining, a comprehensive literature search, 2010 to 2015. There was information from the ECHA website up to this date. All forms of TiO2 was taken into account, and there was reliability principles. The material had to be characterized. There has to be a description of the dispersion of the test material. The papers before 2010 was not taken into account because they were not considered reliable, and there were other details as well that was taken into account. Additional criteria for the acceptance of in vitro studies, in vitro is here indicated by this little petri dish down here. Negative and positive control should be included, validated and known protocols should be used, replicates or independent experiments should be conducted, time point selection was important, and there should be evidence of uptake or cytotoxicity in case of negative results. Well, here a critical person could, of course, say, known or validated protocols, and there is a lot of in vitro COMET assay studies. Are these known or validated protocols? And the in vitro micronucleus assays, were they conducted according to the OECD test guidelines, or were they conducted according to the whatever principles in the lab where they were conducted? Another little stop for consideration could be here, evidence of uptake or cytotoxicity in case of negative results. This is not really a criteria that we normally have to apply to in vitro testing. We test up to a guideline dose level. We see cytotoxicity if we see it, but we are not mandated to demonstrate that there actually is any exposure of the cell. It's not unusual that you test up to a guideline limited dose that for many in vitro systems today is 2,000 milligram per 2,000 microgram per mil, excuse me. You see nothing, but this was the limit dose, and you are supposed to be clear to go. So the in vitro study types that were taken into account was the in vitro micronucleus, gene mutation tests, ChroMab tests, and then the supportive data from the COMET assay. Information of the mechanism of action, especially if the genotoxic effects might be due to some oxidative stress induced by the TiO2. These were the studies, and I hope I did count correctly here. Any error would be on my side. 40 studies of the in vitro studies were excluded, 39 were included. So about half of the reviewed assays were not taken into consideration for the final classification effort. And negative results should only be taken into account when there was evidence of cellular uptake or cytotoxicity. As you can see, most of these are COMET assays. There are in vitro micronucleus assays, and so few of the other ones that they can basically be ignored for purposes of today. In vivo studies, which are indicated by a little rodent down here in the corner, nanoforms seem to induce more positive results than non-nanoforms. Very few studies on microforms were available, and none were fulfilling the review criteria. Very few studies compared the genotoxicity of different crystalline forms of TiO2. No difference as function of crystallinity was noted, and here are references, and there was a higher effect of a rutile form in the Numara 2014 paper. So despite the systematic review, there were still issues about which parameters drive the discrepancies. It could have been the dispersal of the material. It could have been the concentrations and exposure durations selected, the route of exposure, the animal model, the cell and organ examined, and the parameters that were assessed. This is a table of the total amount of in vivo studies that were taken into account. Again, I made this table myself, so any error would be on my side. It kind of looks like you would have 6 studies, but you don't really, because this study, LUORA 2014, is here twice, so is SADIC is here twice, because they looked at different endpoints in the same system. The positive result here came from a Drosophila test with TiO2 that was from Carmona et al., 2015, and I'm not quite sure if I would actually have taken a Drosophila test into account at all or not, but basically you can say that the in vivo results had very little application, I believe, on the final conclusion. So, is TiO2 genotoxic or not? There has been negative results in many studies. There have been positive results in many studies. Negative results. How does one prove a negative? It's starting to be harder and harder. It was a little bit discussed earlier. I do believe you can prove a negative. I think you can prove a negative by proving that it is not positive and clearly showing it. What we have run into recently is that even though we think it's a clear negative, we get responses for agencies saying, yeah, but we don't really think so. So in other words, it could be helpful if everybody would actually follow the mutual acceptance of data criteria, at least for now. If it's in the guideline, it should be the data should be accepted. What we experience is that the study is accepted, but not the data. And then we had to do more testing, and in the end, we had to do in vivo testing, which of course I think everybody would like to avoid today. There's positive results, and then we get into the question of, is this a primary or a secondary mechanism of action? The mechanism of action has been discussed during these days here right now. There is the oxidative stress pathway is probably involved in the genotoxic effects of TiO2, even if a consistent response was not observed among the reviewed studies. This is per ANSES. These studies had inflammation that was not associated with genotoxic effects, but so there was a consideration that the inflammation and oxidative stress alone may not be sufficient to drive to genotoxic effects. And here we come to the other conclusion, that data suggesting that TiO2 may be able to enter the nucleus and directly interact with DNA. So the secondary effect would be the oxidative stress leading to inflammation. Much discussed mechanism of threshold. Let's go to the next slide. The direct interaction with DNA would mean there is an accumulation in the nucleus. For the in vivo studies, Gao et al. Saw an accumulation in the nucleus associated with a genotoxic effect. However, Luro et al. Did see it, but it wasn't associated with a genotoxic effect. there was additional publications, and I found this kind of interesting because there is actually a statement saying that additional publications were not summarized in the report because they were of low quality, but they also reported some accumulation in the nucleus and possible interaction with DNA after in vivo administration, and these two studies are mentioned. For the in vitro studies, did not systematically investigate the accumulation in the nucleus, which doesn't really surprise me because it is not a requirement, and it is certainly not something that we would just go ahead and do. There was no quantification if it was reported, and there is the thought from Carlson that since the nuclear pore complex is less than 8 nanometers in diameter, a direct interaction of DNA could occur during mitosis and interfere with the microtubulus, causing clastogenic effects and perhaps also aneugenic effects. The conclusion statement was that this data suggests that TiO2 can enter into a cell nucleus and directly interact with DNA, maybe. And in summary, the oxidative stress seems to be the main pathway. But the direct genotoxic effect cannot be totally excluded. And I believe we are going to come to this in our discussion part after my presentation, so I will not go into this more right now. However, again, back to the practical testing lab where I come from and where I live, the potential interaction toxicity depend on the composition and size of the TiO2 formulations. Particulates may or may not be soluble in biological matrices that complicates the impact on the potential exposure of target organs and cells. For the nano-sized TiO2, it might allow for movement across biological barriers, and it might potentially allow for access into the cell and into the cellular compartments, including the nucleus. This is furthermore a question if TiO2 can enter accumulate in the cell nucleus. This is basically summarizing, which I already said. I'm throwing out the question at the end, is this a theoretically based concept more than a real concept? This is a cartoon which is really about silver nanoparticles, but it kind of shows how, if you imagine that this would be TiO2, how TiO2 would get into the cell, and instead of having the ionization, you would have the particles actually moving into the nucleus and further down into the cell. Pore solubility and precipitation is a confounding factor. Nanoparticles are very poorly soluble, including TiO2. This means that it's very hard to make an appropriate dosing solution. You get suspensions of non-soluble and particulate matters. So basically, you would like to have a solution. You might get a suspension, and you see how your material falls down here, and it might even be worse. It might all collect here, and you might test us up here, or you might just do sloppy work and not even know what you're testing in the end. You lose material, too. There is incomplete dispersion, sedimentation, dissolution. You can't really ensure contact with the cells. And from this point of view, there is some merit to the statement that if you have a negative result, you should show exposure of the cell. The treatment conditions might be very compromised. You might not be able to remove your material when you want. And the question of exposure is kind of questionable. Which concentrations did we actually use? Precipitation has also been noticed by OECD. This is from the same overview review document, which is saying that it's not specifically included in the test guidelines, but care should be taken when you have an interpretation of a positive result that's only seen at the precipitation concentration. Well, for testing nanomaterials, this can put you in a very interesting place because it might be that you have precipitation on all dose levels until you go so low down that you can ask, is there any meaning of doing the study anymore? Or you end up running experiments with very wide ranges because you need to have a lot of concentration, so you are trying to catch the exactly correct one for your assessment. This is the same slide as I showed before. I am getting towards the end of my presentation here, and I am going to slightly show this one paper here, 2 slides from here. because I found it interesting. They're actually looking at TiO2 as a food additive, and they do see genetic effects of it. What they did, they looked at the food additive E171. They saw induction of frost formation and genotoxicity, and they looked at the contributions of the micro and nano-sized fractions. This was the project. They also used the in vitro COMET and the micronucleus assay. They saw ROS formation and DNA damage using CACO2 cells and the HCT116, which I believe is a cell-free system, actually. The results they got was that all three test substances induced single-strand DNA breaks and ROS generation. It's also induced chromosomal damage, and this is their conclusion. This is a picture from when they're looking at the identification of the interaction with kinetochores. Here are arrows pointing, but I cannot say if they're actually pointing to actual nanoparticles or not. But this is from the paper, which is, of course, available for everybody on the web. And as this is not enough, just when I already arrived at this meeting, there was more notifications coming. There is a brand new paper in Mutagenesis, which is a critical review of challenges associated with advanced in vitro systems used for the study of nanoparticle secondary genotoxicity. So I almost have a feeling that I could be back here after 2 weeks and give an entirely updated presentation based on the papers that has come out in between. This is my last slide. It's kind of wishy-washy. I tried to come up with suggestions of what perhaps could or should be done for the TiO2 genotoxicity. I think one thing would be to make a decision what form to test, bulk, particulate, or nano. Often when this is said, depending on who you represent, your opinion differs. Some people think that if all forms should be equal, we should test the nano. Others think, oh, then we should test the bulk, and the results with the bulk should also apply for the nano. Maybe there should be a conclusive review article. This is thrown out a little bit carefully because there are lots of review articles, but maybe there should be like a 2016 or 2017 paper coming out. There probably should be some consideration around the inconclusive CLP classification. Is it going to remain as inconclusive, or is this going to prompt more research work perhaps, or more work? And how is this actually going to be viewed by different companies who has to do the labeling? And there is the big question of the uptake and internalization into the nucleus. Is it an artifact or an effect? It's a huge challenge if you want to characterize biodistribution of TiO2 on a cellular and subcellular level. And there is the question of the direct binding with DNA. Is it this one that works, or is it a secondary effect of oxidation? And this is the end of the presentation. There is my email in case somebody wants to communicate afterwards. Thank you.
Thank you for a nice presentation. I have a general question about in vitro test mutagenicity assays. How do you consider, or do you consider at all, that in vitro you are dealing with a static system and very acute effects, whereas in vivo, in a dynamic system, you are mostly considered chronic effects?
We do consider it in the sense that the established test systems have time points for when you are supposed to look at your effect, because it is a dynamic effect, as correctly said. It means that if you let your cells grow too long, for example, you lose the effect because the cells divide and might get rid of it. But otherwise, I don't think we really take it into account. They're considered to be short-term screening tests.
Because of the acuteness, you are probably dealing with high doses compared to what is actually happening in vivo.
Yes.
So that's
there's basically, as far as I know, no real relation between the dose in vitro and in vivo. The doses for in vitro are set based on what is known about the test system and based on empirical knowledge of how low can you go in your top concentration without necessarily missing something. Yes.
Yeah.
Okay. Jan Prochaska. 14.
I have a general comment to those studies. When we did the review, we found actually only one study that takes into account the IR reflection, very high reflection of titanium dioxide. And when you use red dyes to evaluate the changes in color for these experiment genotoxic or mutagenic, then those are all clipped by the IR reflection.
I don't really have a comment. Thank you.
Okay.